Earth is not safe. But compared to what we have found out there, Earth is a retirement home. In the last 3 decades, astronomers have confirmed more than 5,500 planets beyond our solar system. Most of them are alien enough to strain imagination. But a handful are so extreme that the word hostile does not begin to cover it. These are places where the weather kills before you register it. Where the planet itself is dying. Where the basic materials you are made of cannot hold together in the heat. You are going to 5 of them. The first one looks familiar from a distance. HD 189733b sits 63 light-years from Earth. From a telescope, it appears blue. The kind of blue that on Earth means ocean. Means breathable air. Means something you could move toward. That is not what this blue means. The color comes from silicate particles suspended in the upper atmosphere. Silicate is glass. The atmosphere of HD 189733b. Wind speeds on this planet reach 5,400 miles per hour. That is 7 times the speed of sound. The fastest wind ever measured on Earth was 253 miles per hour, recorded during a tropical cyclone in 1996. That was enough to strip buildings from the ground. The winds on HD 189733b are 21 times faster than that. At high altitude, where the temperature drops slightly, the silicate particles condense. They form droplets. And those droplets, driven by winds moving at 5,400 miles per hour, travel sideways. Not down toward any surface. Sideways. What falls on HD 189733b is not rain in any sense your nervous system has a category for. It is a horizontal blizzard of glass shards moving at the speed of a hypervelocity round in every direction at once. The surface temperature exceeds 1,000 degrees Celsius. There is no solid surface to stand on. But if there were, you would not survive long enough to notice the glass. The heat would reach you first. Then the pressure of the dense, torched atmosphere. Then the radiation from the nearby star completing the argument. From space, this planet is blue. That is the last pleasant thing you can say about it. Here is the thing that makes HD 189733b particularly useful as a starting point. It is close. 63 light-years is a short distance by galactic standards. This planet is in our neighborhood. It is one of the most studied exoplanets precisely because of that proximity, and because Hubble could resolve its atmospheric color directly. What we know about it is not speculation drawn from a distant signal. It is well observed. The glass rain is not a hypothesis built on one data point. It is the atmospheric reality of a world that has been scrutinized from multiple telescopes across multiple wavelengths over 2 decades. The reason that matters is this: if a planet this violent exists this close to us, the distribution of planetary conditions across the rest of the galaxy does not favor comfort. HD 189733b is not an outlier. It is a sample. Now take a planet twice the size of Earth, orbiting its star in 18 hours. That planet is called 55 Cancri. It is 41 light-years away. It orbits so quickly, and so close to its star, that the same face always points toward the heat. There is no dawn on 55 Cancri. No rotation you would recognize. No sunset. There is a day side and a night side, and the line between them is permanent. On the day side, the most recent James Webb measurement puts the surface temperature at roughly 1,500 degrees Celsius. At that temperature, rock does not stay solid. Rock melts. Observations from NASA's Spitzer Space Telescope, extended by the James Webb Space Telescope in 2024, indicate that the day side of 55 Cancri is covered in a global ocean of magma. Not volcanic hotspots. Not isolated lava flows. A planet-spanning ocean of melted rock. Imagine standing at the boundary between day and night. Behind you, the ground is liquid. The heat radiates with enough intensity that the air itself carries a faint luminescence. In front of you, the night side sits at around 1,300 to 1,400 degrees Celsius. That is the cold side. It is cold only by the standards of this particular world. The James Webb Space Telescope detected signs of a volatile atmosphere around 55 Cancri, suggesting that gases outgassed from the magma ocean may be sustaining a thin shell of chemistry above the surface. This does not make the planet livable. It makes it more geologically active than any world we have ever catalogued. You would not reach the Terminator line. You would be part of the ocean before you crossed it. In 2008, astronomers discovered a gas giant called WASP-12b, roughly 1,400 light-years from Earth. It is about 1.4 times the mass of Jupiter, but nearly twice Jupiter's radius. The extra volume is not because the planet formed large. It is because something is pulling it apart. WASP-12b orbits its star in 26 hours. At that distance, the star's gravity does not act on the planet evenly. The side of the planet facing the star feels a far stronger pull than the far side. The difference is large enough to deform the planet out of a sphere. WASP-12b is not round. It has been stretched into an egg shape, the near side bulging toward the star that is in the process of claiming it. Atmospheric material is being pulled away from the planet, continuously and irreversibly. That material forms a thin disk around the star, a ring of stolen gas in a widening orbit. The planet's orbit is also decaying. Astronomers have measured the time between each planetary transit with enough precision to detect a shortening of 29 milliseconds per year. The planet is moving closer. Not by much each year, but by enough that the direction is unmistakable. Models based on this decay rate suggest WASP-12b will be consumed entirely in roughly 3 million years. Against the typical lifetime of a planetary system, that is a short time. 3 million years ago, early humans were shaping stone tools on Earth. By astronomical standards, WASP-12b is already in its final chapter. The dayside temperature is approximately 2,700 Kelvin, over 4,400 degrees Fahrenheit. The atmosphere glows. You are not watching a planet that might one day become dangerous. You are watching a planet that is already past the point of return, falling by 29 milliseconds per year toward an ending that was decided the moment it formed too close. In 2020, a team of astronomers used the Very Large Telescope in Chile to study a gas giant 640 light-years away in the constellation Pisces. The planet is called WASP-76b. The day side of WASP-76b receives thousands of times more radiation than Earth receives from the Sun. The temperature there exceeds 2,400 degrees Celsius, hot enough to vaporize iron. Iron, the element that forms the solid core of our planet, enters the gas phase in the atmosphere of WASP-76b on its sun-facing side. The research team detected iron vapor at the evening boundary of the planet, the edge where the day side transitions toward night. On the morning side, no iron signal was found. The night side, cooler at around 1,500 degrees Celsius, is cold enough by comparison for iron to condense. The leading interpretation of this asymmetric detection is that iron falls out of the atmosphere on the night side, precipitating as metallic droplets. As the lead astronomer David Ehrenreich described it, one could say this planet gets rainy in the evening, except it rains iron. This interpretation remains the best current explanation for a confirmed observational signature. The asymmetric iron signal is real. The mechanism behind it is the subject of ongoing research. But the conditions that make such a process plausible, a world hot enough to vaporize metal on one face and cool enough to precipitate it on the other, those conditions are not in dispute. If you were standing on the night side of WASP-76b, you would be in an atmosphere carrying metallic vapor, on a world where even the cooler hemisphere is hotter than any furnace ever built on Earth. The evening air on this planet is iron. What makes WASP-76b useful to hold in mind is that it is not unique in having extreme atmospheric chemistry. It is unique in that we can measure it. The ESPRESSO instrument on the Very Large Telescope is sensitive enough to detect the spectral fingerprint of iron vapor across 640 light-years of space. The fact that we can do that at all is remarkable. And it means that every world in this episode was discovered not because it is an exception, but because we finally built instruments capable of seeing what was always there. Now consider the hottest exoplanet ever confirmed. KELT-9b was announced in June 2017. It is a gas giant 2.8 times the mass of Jupiter, orbiting its star in approximately 1.5 days. The dayside temperature exceeds 7,800 degrees Fahrenheit, which is 4,600 Kelvin. Most known stars are cooler than the surface of this planet. Read that again, slowly. A planet. Not a star. A world. And its surface outpaces most stars in this galaxy in terms of heat. The consequences of that temperature are not just extreme. They are categorical. Water cannot form on the dayside. Carbon dioxide cannot form. Methane cannot form. The ultraviolet radiation from the nearby star tears Hydrogen molecules, the most basic building blocks of a gas giant's atmosphere, are ripped into individual atoms on the dayside and can only reform on the slightly cooler night side. The chemistry of KELT-9b's dayside more closely resembles the interior of a star than the surface of any other planet we know. The host star, KELT-9, is nearly twice the temperature of our Sun. It is likely eroding KELT-9b through constant irradiation, stripping the outer atmosphere over time. The planet and the star are locked in a relationship with one obvious ending. At 4,600 Kelvin, the question of what you would experience there does not have a useful answer. There is no material, no vehicle, no configuration of matter that approaches KELT-9b intact. The category of environment this world occupies is one the universe reserves for stars. In this case, it simply drew the boundary poorly. 5 planets. 5 different ways that the same physics that built this solar system arranges itself into something lethal. Here is the part worth sitting with. Every one of these worlds was here before we knew about it. HD 189733b was raining glass at 5,400 miles per hour for billions of years before a telescope in Chile made note of it. 55 Cancri E has been a global magma ocean for longer than complex life has existed on Earth. WASP 12b has been dying, slowly and measurably, since long before there were eyes to see it. The universe did not become terrifying when we found it. We just started paying attention. 30 years ago, we had 0 confirmed planets beyond this solar system. None. The count now exceeds 5,500. The instruments we use have improved to the point where we can detect iron vapor in an atmosphere 640 light-years away, and we can measure a planet's orbital decay 29 milliseconds per year at a time. Which means none of these discoveries are conclusions. They are openings. Each one raises the same question: how many more are out there, and how extreme do they get before we reach the edge of what is possible? The data so far suggests we have barely started asking. Earth has one thin layer of breathable air. Wind. One orbit, stable enough for liquid water across billions of years. By the standards of what we have now confirmed, that is not the default condition of a planet. That is a specific and improbable outcome set against a backdrop of worlds that would end you before you could form a thought about it. Earth is not safe. The crust moves. The climate shifts. The sun will eventually expand and swallow this planet whole. But compared to a world where glass rains sideways through winds moving at 7 times the speed of sound, where the surface is a global ocean of melted rock, where a planet is being stretched into an egg and pulled apart by its own star, where iron evaporates on one hemisphere and falls as metal on the other, where the air temperature exceeds the surface of most stars in the galaxy, Earth is a retirement home. There is one more thing worth naming before you close this. All of these planets were discovered by looking for the ways they affect their stars. A planet transiting in front of a star dims the light by a fraction of a percent. A planet's gravity tugs on its star in a pattern we can measure in the star's spectrum. Can never survive, through the faint shadows and wobbles they leave behind. And from those shadows, we have reconstructed glass storms, magma oceans, iron rain, orbital decay time to 29 milliseconds, and surface temperatures that exceed the outer layers of stars. This is what the first generation of exoplanet science looks like. We are not done. We are barely past the first page. The question worth holding on to is this: if these are the worlds we have found so far, what are we going to find next?